Hi, my name is Tamay and I want to present our work where we tackle the problem of providing an omnidirectional, three-dimensional impression of a remote scene during a Telepresence session. We use two cameras mounted on an electromechanical pan tilt unit, so a PTU, to mimic the 2 degrees of freedom of the user's head motion and provide stereoscopic imagery in every viewing direction. The aggregated latencies in such a system, including the communication delay, is a limiting and quality-reducing factor and will provoke the emergence of motion sickness. We apply a delay compensation approach together with a novel head motion prediction to compensate the lag between head motion and the reflected visual response and thus prevent the user from experiencing visual discomfort. The core idea is to capture slightly more imagery than actually displayed to the user. By using only a subset of the camera's field of view, we are able to use the residual imagery as a buffer. When the user rotates the head, the view orientation can be changed locally without noticeable delay until the camera system follows and the updated frame arrives. We use the so-called compensation rate as a metric, ranging from 0 to 1 or 0 to 100% to describe the achievable level of delay compensation. To further improve the level of compensation, we propose a novel head motion prediction approach to send the estimated delayed head orientation rather than sending the current position. We compare our approach to state-of-the-art solutions and prove its superiority. Our predictor is based on 3 components. The first component considers past data and uses the weighted least squares method to fit a first-order polynomial function. The second term uses a Kalman filter to estimate the current state of the head, being the current orientation, the angular velocity, and acceleration. This optimal state estimate is applied to a constant acceleration model for extrapolation. The last component is a balance term and alleviates the effect of overshoot. The weighted sum of these 3 terms determines the predicted value. We built a head motion dataset with 30 participants to train the weights and evaluate our approach under real conditions. Here we show the first version of our PTU camera system, mimicking the user's head movements. For a meaningful and reproducible evaluation, however, we used an available omnistereoscopic video source and the aforementioned real head motion dataset. On the remote side, we have either the PTU or the omnidirectional video source, and on a local side, we have the user wearing a head-mounted display to immerse him or herself into the remote environment. Without delay compensation, the video will always lag the user's head motion. Applying the delay compensation allows for an instantaneous response to the movement of the user's head. In this slide, we give an overview of the obtained results. We demonstrate the level of compensation for the pan rotation of an arbitrary head motion profile. For cases where no compensation is present, where delay compensation is applied, and where delay compensation is combined with our head motion predictor. It can clearly be seen that the prediction approach significantly helps to further improve the level of delay compensation. If your interest is raised or if you have any questions, feel free to reach out to me during the poster session.